Secrets of the Earth. It breathes, it churns, it protects. You know it as Earth. Scientists know it as one of the most dynamic geological laboratories in the universe. Now, with the help of new satellites, deep ocean submersibles, and sophisticated seismic networks, scientists are seeing our planet as they never have before and even recreating what happens in its molten core in laboratories across the globe. Their work will help us understand aspects of Earth that have puzzled scientists for generations. But more critically, it may help us predict earthquakes, volcanic eruptions, and climate shifts that have the power to reshape continents, alter civilizations, and transform life as we know it. Such catastrophic events have happened before, but never with 8 billion people calling this planet home. Secrets of the Earth reveals a profound new understanding of our home world, one that might help us protect it for generations to come. April 22nd, 2016. Off the coast of Ecuador, deep beneath the Pacific Ocean floor, something stirs. The tectonic plates that have been locked together for decades suddenly release. In an instant, a segment of the Earth's crust the size of Connecticut lurches 23 feet. The ground above convulses. Buildings crumble. 700 people lose their lives. But this is more than just another earthquake. This is Earth revealing its secrets. When seismologists look at the data from their instruments, they're not just seeing the earthquake itself. They're seeing into the Earth, thousands of miles down, watching how energy moves through our planet's interior. It's like having X-ray vision into the very heart of our world. The Earth beneath our feet is far from solid. It moves, it flows, it transforms. The ground you stand on today was once at the bottom of an ancient ocean. The mountains you see were once flat plains. The continents themselves are travelers, drifting across the globe at the speed your fingernails grow, leaving trails of earthquakes and volcanoes in their wake. Beneath the thin crust we live on lies the mantle, a layer of rock so hot it behaves like thick honey, flowing in massive convection currents over millions of years. Below that sits the outer core, a churning sea of molten iron and nickel, spinning at nearly 1,000 miles per hour, generating the magnetic field that shields us from deadly solar radiation. And at the very center, under pressures 3 million times greater than at the surface, lies the inner core, a solid ball of iron nearly as hot as the surface of the sun. The inner core is growing. Every year, it gets a little bit bigger as iron crystallizes out of the outer core. And as it grows, it releases heat that drives the convection in the outer core, which generates our magnetic field. Without this process, Earth would be a very different place. There would be no protective magnetic shield, no defense against the solar wind that would strip away our atmosphere. Life as we know it could not exist. It is a different place, at least it was. 4.5 billion years ago, Earth was born from a disk of gas and dust swirling around the young sun. In those violent early days, the planet was bombarded by asteroids and comets. One impact was so catastrophic, it sent a chunk of Earth spinning into space. That chunk became our moon. The young Earth was hellish, a molten ball of rock with no atmosphere, no oceans, no life. But slowly, over hundreds of millions of years, it transformed. Volcanoes belched gases that formed the first atmosphere. Comets brought water that condensed into the first oceans. And then, roughly 3.5 billion years ago, something extraordinary happened. Life emerged. The earliest life on Earth was microbial, and these microbes didn't just passively exist on our planet. they transformed it. They began producing oxygen through photosynthesis, completely changing Earth's atmosphere and paving the way for complex life. Over billions of years, these tiny organisms turned Earth from a world with barely any oxygen into one where oxygen makes up 21% of the atmosphere. This was Earth's first great transformation, but it would not be its last. The planet has been in constant flux, cycling through ice ages and warm periods, mass extinctions, and evolutionary explosions. The continents have collided and split apart multiple times, forming supercontinents that lasted for hundreds of millions of years before breaking up again. 250 million years ago, all of Earth's land masses were joined together in a supercontinent called Pangaea. Then, driven by the relentless convection in the mantle below, Pangaea began to crack. The Atlantic Ocean was born as the Americas drifted away from Europe and Africa. India broke free and crashed into Asia, thrusting up the Himalayas. Australia separated from Antarctica and headed north. These movements continue today. GPS satellites can measure the continents drifting in real time. North America is moving away from Europe at about the same rate your hair grows. But this slow dance of continents has consequences. Where plates collide, mountains rise. Where they pull apart, new ocean floor is created. And where they slide past each other, earthquakes tear cities apart. Every earthquake changes the stress on surrounding faults. A big earthquake in one place can make earthquakes more likely somewhere else, sometimes hundreds of miles away. Scientists are beginning to understand these relationships, but they still can't predict exactly when or where the next big one will hit. May 12, 2008, Sichuan Province, China. A massive earthquake, magnitude 7.9, strikes without warning. 90,000 people die. The quake is so powerful it's felt 1,500 miles away. In the aftermath, scientists discover something troubling. The earthquake occurred along a fault that had been quiet for thousands of years. There had been no warning signs, no smaller earthquakes building up to the main event. The Earth had kept it secret until it was too late. This is the challenge facing seismologists around the world. Unlike hurricanes or volcanic eruptions, earthquakes give almost no warning. By the time the first tremor is felt, the earthquake has already begun. Scientists are trying to understand the precursors to earthquakes, the subtle changes in the Earth that might occur before a major event. They're measuring ground deformation with GPS, changes in groundwater levels, variations in the Earth's magnetic field. But so far, reliable earthquake prediction remains out of reach. But prediction isn't the only tool in our arsenal. In recent decades, scientists have developed early warning systems that can detect an earthquake the moment it begins and send alerts to cities in its path. The warning comes seconds before the shaking arrives. Not much time, but enough to stop trains, shut down power plants, and give people time to take cover. Japan has the most sophisticated earthquake early warning system in the world. On March 11th, 2011, it proved its worth. When the Tohoku earthquake began, the system detected it immediately. Warnings went out across Japan. People had between a few seconds and a minute to prepare, depending on how far they were from the epicenter. The Tohoku earthquake was magnitude 9.0, one of the most powerful ever recorded. The shaking lasted for 6 minutes. But the earthquake itself was just the beginning. The real devastation came from what followed. The earthquake occurred offshore, where the Pacific Plate dives beneath the North American Plate. The quake thrust the seafloor upward by as much as 30 feet, displacing an enormous volume of water. Within minutes, a tsunami was racing across the Pacific at the speed of a jet airliner. The waves that hit the Japanese coast were over 100 feet tall in some places. They swept away entire towns, killed more than 18,000 people, and triggered a nuclear disaster at the Fukushima power plant. The tsunami was so powerful, it was detected on tide gauges around the world. It even reached the coast of Antarctica. Tsunamis are different from normal ocean waves. Normal waves are caused by wind and affect only the surface. Tsunamis involve the entire water column, from the seafloor to the surface. That's why they're so destructive. They carry enormous amounts of energy, moving entire layers of the ocean across vast distances. The Pacific Ocean is ringed by the Ring of Fire, a 40,000-kilometer horseshoe of volcanic arcs and ocean trenches where roughly 90% of the world's earthquakes occur. It's here that tectonic plates collide, and it's here that Earth's most powerful forces are unleashed. But the Ring of Fire isn't just dangerous, it's also creative. The subduction zones, where plates dive into the mantle, are the birthplace of new continental crust. Water carried down by the descending plate causes the mantle above to melt, generating magma that rises to form volcanoes. Over millions of years, these volcanoes build up into mountain ranges and even entire continents. Subduction zones are like giant recycling machines. Old ocean floor goes down, and new continental material comes up. Without this process, we wouldn't have the continents we have today. The cycle is endless. Destruction creating creation, death birthing life. April 14th, 2010. Age of geological volcano in Iceland erupts. Ash and steam shoot 50,000 feet into the air. The eruption itself isn't particularly large, but it brings Europe to a standstill. Airlines cancel more than 100,000 flights. 10 million passengers are stranded. The economic cost exceeds $5 billion. This is a reminder that we live on an active planet. There are roughly 1,500 potentially active volcanoes on Earth, and at any given time, about 50 of them are erupting. Most are far from population centers, but some threaten millions of people. The challenge with volcanoes is that each one is different. Some give clear warning signs before they erupt. Others don't. Scientists need to monitor them constantly, looking for changes in seismic activity, ground deformation, gas emissions, anything that might tell them an eruption is coming. But understanding individual volcanoes isn't enough. Scientists are now looking at the bigger picture, studying how volcanic eruptions can affect the entire planet. 75,000 years ago, Mount Toba in Indonesia erupted in one of the largest volcanic events in Earth's history. The eruption ejected nearly 700 cubic miles of ash and rock into the atmosphere. Global temperatures dropped by as much as 20 degrees Fahrenheit. The volcanic winter lasted for years. Some scientists believe this eruption brought humanity to the brink of extinction, reducing the human population to just a few thousand individuals. Supereruptions like Toba are rare, but they do happen. The geologic record shows they occur roughly every 50 to 100,000 years. We're overdue for another one. But when it will come, nobody can say. Beneath Yellowstone National Park in Wyoming lies one of the planet's largest supervolcanoes. It's erupted 3 times in the past 2 million years, most recently 640,000 years ago. Each eruption was catastrophic, covering much of North America in ash. When will it erupt again? No one knows, but scientists are watching. Seismometers, GPS stations, and other monitoring equipment are spread throughout Yellowstone, constantly measuring the activity beneath the park. The ground rises and falls as magma moves around below. Thousands of small earthquakes occur every year. But this doesn't mean an eruption is imminent. The system might stay dormant for hundreds of thousands of years, or it might not. While supervolcanoes sleep beneath our feet, the Earth's surface is undergoing another transformation, one driven not by geology, but by climate. For most of Earth's history, the climate has been warmer than it is today. There have been periods when there was no ice anywhere on the planet, when palm trees grew in Antarctica, when sea levels were hundreds of feet higher than they are now. But for the past 2.5 million years, Earth has been in an ice age, with massive ice sheets advancing and retreating across the continents in cycles lasting roughly 100,000 years. The ice cores drilled in Greenland and Antarctica are like time machines. They contain tiny bubbles of ancient atmosphere trapped in the ice. By analyzing these bubbles, scientists can measure the composition of the atmosphere going back 800,000 years. They can see exactly how carbon dioxide, methane, and temperature have changed over time. What the ice cores reveal is striking. For hundreds of thousands of years, carbon dioxide levels in the atmosphere fluctuated between about 180 parts per million during ice ages and 280 parts per million during warmer periods. The pattern was remarkably regular, driven by changes in Earth's orbit around the Sun. But something changed in the past 200 years. Carbon dioxide levels have shot up to over 420 parts per million, far higher than at any point in the ice core record. The cause is clear: human activity. We're burning fossil fuels at a rate that's adding billions of tons of carbon dioxide to the atmosphere every year. The Earth's climate has always changed naturally, but what we're seeing now is different. The rate of change is unprecedented. We're conducting a massive experiment with our planet's atmosphere, and we don't fully know how it will turn out. The consequences are already visible. Global average temperatures have risen about 2 degrees Fahrenheit since the late 19th century. Arctic sea ice is shrinking. Glaciers around the world are retreating. Sea levels are rising. Weather patterns are shifting. But the Earth has experienced rapid climate change before. 56 million years ago, a massive release of carbon into the atmosphere caused global temperatures to spike by about 9 degrees Fahrenheit in just a few thousand years. This event, called the Paleocene thermal maximum, transformed the planet. Tropical forests spread to the Arctic. Many species went extinct. The oceans became more acidic. It took hundreds of thousands of years for the climate to stabilize. The Paleocene thermal maximum shows us what can happen when you add a lot of carbon to the atmosphere quickly. The planet warms, ecosystems are disrupted, species go extinct. The recovery takes a very long time. It's a cautionary tale for our current situation, written in the rocks beneath our feet. The Earth's climate is intimately connected to its oceans. The oceans absorb about 90% of the excess heat trapped by greenhouse gases. They also absorb about a quarter of the carbon dioxide we emit. This has kept the atmosphere from warming even more, but it comes at a cost. As seawater absorbs carbon dioxide, it becomes more acidic, threatening marine life, especially organisms like corals and shellfish that build shells and skeletons from calcium carbonate. Ocean acidification is sometimes called the other carbon dioxide problem. We don't see it as easily as we see climate change, but it's potentially just as serious. If the oceans become too acidic, it could devastate marine ecosystems and the millions of people who depend on them for food and livelihoods. But the oceans don't just absorb heat and carbon, they also move them around. Ocean currents act like a giant conveyor belt, transporting warm water from the equator toward the poles and cold water from the poles back toward the equator. This circulation helps regulate Earth's climate, keeping some regions warmer and others cooler than they would otherwise be. The most important part of this system is the Atlantic Meridional Overturning Circulation, also known as the Gulf Stream system. Warm surface water flows from the tropics toward the North Atlantic. As it cools and becomes saltier through evaporation, it becomes denser and sinks to the ocean floor, where it flows back south. This circulation delivers enormous amounts of heat to northwestern Europe, keeping it much warmer than other regions at the same latitude. There's evidence that the Atlantic overturning circulation is slowing down. As Arctic ice melts and more fresh water enters the North Atlantic, it becomes less dense and doesn't sink as readily. If this circulation weakens significantly, it could have profound impacts on climate, particularly in Europe. Some regions could actually cool even as the planet as a whole warms. The Earth's climate system is incredibly complex, with countless feedback loops and tipping points. Understanding it requires monitoring the entire planet, its atmosphere, oceans, ice sheets, and land surface continuously and simultaneously. That's where satellites come in. Over the past few decades, Earth observation satellites have revolutionized our understanding of the planet. They measure sea surface temperature, atmospheric composition, ice sheet thickness, vegetation cover, and dozens of other variables. They provide a God's eye view of a planet in constant change. Satellites are absolutely essential for understanding Earth's climate. They give us global coverage and continuous monitoring that would be impossible any other way. Without satellites, we'd be flying blind, unable to see the big picture of how our planet is changing. But satellites alone aren't enough. To truly understand Earth, we need to look inside it. That's where seismology comes in. Every earthquake sends waves rippling through the Earth's interior. By measuring how these waves travel, seismologists can map the structure of the planet's interior with remarkable precision. It's like doing a CT scan of the entire Earth. Seismic tomography has revealed all sorts of structures deep inside the Earth. Scientists can see where the mantle is hotter or cooler, where it's flowing up or down. They've discovered massive blobs of dense material sitting at the bottom of the mantle, remnants of ancient tectonic plates that sank there millions of years ago. These discoveries are reshaping our understanding of how the Earth works. The mantle isn't a uniform layer. It's full of complexity. There are plumes of hot material rising from near the core, like the one beneath Hawaii that's been producing volcanoes for millions of years. There are slabs of cold, dense rock sinking down from the surface, remnants of ancient oceans. And at the boundary between the outer core and the mantle, nearly 2,000 miles down, there's a mysterious region where seismic waves slowed down dramatically. Scientists call it the D-double-prime layer, and they're still trying to figure out exactly what it is. The D-double-prime layer is one of the most enigmatic regions of the Earth. It's very thin, only about 100 miles thick, but it seems to play an important role in how heat escapes from the core. It might be where mantle plumes originate, those massive columns of hot rock that rise from deep in the Earth to create volcanic hotspots like Hawaii and Iceland. Understanding Earth's interior isn't just an academic exercise. The convection in the mantle drives plate tectonics, which causes earthquakes and volcanic eruptions. The circulation in the outer core generates the magnetic field that protects us from harmful solar radiation. If we want to understand the hazards our planet poses and the resources it provides, we need to understand what's happening deep inside it. But perhaps the most profound mystery about Earth isn't in its interior or its atmosphere or its oceans. It's on its surface. How did this planet, this one planet among billions in our galaxy, become a haven for life? The answer lies in a remarkable series of cosmic coincidences. Earth orbits at just the right distance from the Sun for liquid water to exist on its surface. It's large enough to hold onto an atmosphere, but not so large that the atmosphere becomes crushing. It has a magnetic field that shields the surface from deadly radiation. It has a large moon that stabilizes its rotation and creates tides that may have been crucial for the origin of life. And it has plate tectonics, which recycles nutrients and regulates the climate over geological timescales. When you look at all the factors that make Earth habitable, you realize how special it is. We're starting to find other planets around other stars, and we're learning that Earth-like planets might be common in the universe. But planets that actually have life, that might be much rarer. Earth may be 1 in a billion or 1 in a trillion. In the search for life beyond Earth, our home planet is the only example we have. Understanding how life arose here, how it has survived multiple mass extinctions, and how it has shaped the planet itself is crucial for understanding where else life might exist. And life has shaped this planet profoundly. The oxygen we breathe was produced by photosynthetic organisms. The fossil fuels we burn were once living things. Even the rocks beneath our feet contain the remains of ancient life. In a very real sense, Earth isn't just a planet with life on it. It's a living planet where life and the physical environment are intimately intertwined. Life doesn't just adapt to its environment, it actively modifies it. The atmosphere we have today is not the atmosphere Earth would have without life. Life has regulated the planet's temperature, its chemistry, its very habitability for billions of years. It's a partnership between the living and the non-living, a dance that's been going on since life first emerged in Earth's ancient oceans. But now one species, our species, has become powerful enough to change the planet in fundamental ways. We've altered the atmosphere's composition. We've transformed vast swaths of land. We've changed the chemistry of the oceans. We've driven countless species to extinction. And we've done all of this in just a few centuries, the blink of an eye in geological time. The question now is, what will we do with this power? Will we continue down a path that could make Earth less habitable, not just for other species, but for ourselves? Or will we use our understanding of how this planet works to become better stewards of it? We have a choice. We can continue with business as usual and face increasingly severe consequences, or we can take action to reduce our impact on the planet. The science is clear about what's happening and what we need to do. The question is whether we have the will to do it. Time is running out, but it's not too late. The Earth is not static. It never has been. It's a dynamic, evolving system, constantly changing on timescales from seconds to billions of years. Understanding these changes, from the shifting of continents to the fluctuation of climate, from the eruption of volcanoes to the flickering of the magnetic field, is one of the great scientific challenges of our time. But it's also urgent. We share this planet with 8 billion other people and countless other species. The choices we make today will determine what kind of planet we leave to future generations. As we've seen, Earth keeps many secrets, but with each passing year, we uncover more of them. We peer deeper into its interior, higher into its atmosphere, further back into its past. With every discovery, we gain not just knowledge, but responsibility. This planet has been here for 4.5 billion years. It has survived asteroid impacts that would make nuclear weapons look like firecrackers. It has endured ice ages that buried continents under miles of ice. It has weathered volcanic eruptions that darkened the sky for years. It has bounced back from mass extinctions that wiped out 90% of all species. Earth is resilient, but it's not invincible. And we, as the first species in its long history to truly understand how it works, have a choice to make. We can use that understanding to protect it, or we can continue to push it past its limits. The Earth will survive us, one way or another. The question is, will we survive ourselves? The answers lie in the secrets we continue to uncover, in the data streaming back from satellites, in the signals from seismometers deep underground, in the bubbles of ancient air trapped in ice, and the fossils embedded in rock. Each piece of information is a clue, a glimpse into the workings of the most complex, dynamic, and precious planet we know. This is Earth. It breathes, it churns, it protects. And now, more than ever, it needs us to understand it, to respect it, and to ensure that its secrets and its wonders endure for billions of years to come.